Welcome to Learn with Dina. Today on topic solidification in a liquid to solid transformation of a crystalline structure, we will study how does the properties, microstructure and phase transformation are relevant. There are various types of phase changes. It can involve state of aggregation, which is transformation from liquid to solid, and crystal structure such as transformation from BCC to FCC or any other. Also the compositions. Change in composition is a long range diffusions. Atoms need to travel through a thousands of interatomic distance, and so this study is also a full relevant. The two basic mechanisms involved are nucleation and growth mechanism and sphenoidal decomposition. Diffusion in solid is the mass flow process in which atoms changes their position relative to the neighbors in a phase under influence of thermal energy and concentration gradient. As given by Fick's law, the first law on steady state tells that the diffusion flux is directly given by negative of diffusion coefficient with the concentration gradient. And the second law on non-steady state tells that the change in concentration with the time is given by diffusion coefficient and the square the differential of the concentration gradient. Depth of penetration is given by square root of diffusion coefficient times the, as given by the atomic model of diffusion. There are two types of diffusion occurs in the atoms. One is interstitial diffusion, the other is substitutional diffusion. As given here, the diagrams of sphere model of atoms arranged in a row and column wise manner, and each sphere is an atom. For the interstitial diffusion, the atom jumps from one interstitial site to the another. In executing a unit step, the activation energy is simply the energy barrier along the path from the one side to the next. Any atom of radius which could fit in this interstitial site can take a position, and it can travel along various interstitial site which is available on gaining or releasing the energy. In the other side, the substitutional diffusion, the atom jumps from one regular site to the any other vacant position. In addition to the probability of an atom crossing the activation barrier along the path, probability of neighbor site being a vacant has also taken into account. The magnitude of substitution is always less than the magnitude of interstitial. As given by the diffusion coefficient, The diffusion is larger in grain boundaries than the for the lattice as the pro-exponential constant of diffusion. However, the cross-sectional area across which the mass transfer occur is less for grain boundaries. At high the temperature, lattice diffusion becomes important. Nucleation and growth kinetics. When free energy of parent phase become higher than the product phase, then phase changes occurs and rises by driving force. As given by the graph in which the free energy along the y direction and temperature along the x direction, growth of the liquid and solid, and the difference in G del G can become negative when the temperature is above melting point. Liquid can spontaneously transform to solid. Formation of very tiny particles that are stable to further thermal fluctuation and will not dissolve is called as the nucleation, and increase in the size of this particle by transfer of atoms is called the growth. When del G less than 0, it means the Gs minus Gl is less than 0, that is Gs is less than Gl. So below melting point temperature, the diffusion is below the melting point. The liquid transforms to solid and very tiny particles gets nucleated, and there is an increase in size. And this nucleation can be divided into two types such as homogeneous nucleation and heterogeneous nucleation. What is homogeneous nucleation? Probability of nucleation remains constant throughout the volume of parent phase. Free energy as given by the formula where the r is the radius of the sphere and sigma is the specific surface energy. The graph is between the free energy and the temperature, and it is studied for various temperature T1, T2 and T3. The temperature are in the range of T0 as the greater and T3 as the lower one, and T0 is the temperature used to study this curve. When driving force exists, del G is usually negative and sigma is positive. And so we can find the driving force and the radius at critical point. What is this critical point? So at each temperature, the free energy rises to its maximum, returns to zero value. And these points are called critical nucleation barrier, or it can also be called as activation free energy of nucleation. The barrier to the nucleation is overcome with the aid of thermal fluctuation. At temperature greater than T naught with equilibrium, del F is infinite and nucleation rate is 0. At 0 temperature, there is no thermal fluctuation and nucleation is again 0. At equilibrium temperature T naught, del F is infinite and nucleation rate is zero. We'll elaborate this statement with another graph between the change in temperature with I and U. I stands for nucleation rate and U stands for the growth rate. So when there is a change in temperature, for the initial change, we start to form the initiation, and initiation is maximum at some point in a range, and where the growth is very low, and growth starts to grow to a maximum at some point at high temperature range, and which also start to drop down to a lower value. This range 1 is the point where we get high initiation and low growth rate. So we finally get finer grains at this temperature difference 1, and the section 2 where there is high growth but low initiation, which tends to a coarser grain, and it offers at the temperature range 2, which is greater than the temperature range 1. So if we maintain at lower the temperature difference, we get fine grains, and larger the temperature difference, we get coarse grains. We move on to the heterogeneous nucleation. The preferred sites show nucleation greater than other sites. So what are the sites? In case of liquid, our sites are the walls of the container, and in case of the solid, the sites includes inclusion, grain boundaries, staking faults, and dislocation. So as shown by the figure, let's consider this as the beta phase, and this the alpha phase, and that's the delta phase. So there's a tension force exists between the phase. The nucleation of beta on surface of del with parent alpha is schematically shown. Theta determine the angle of tension force acting at the periphery of beta particle, and the energy inclusion surface is utilized during the nucleation. Del F net decreases when theta decreases, so the crystal of alpha and beta are similar. In the overall transformation rate as given by dx by dt, which is the function of nucleation and growth, x is the fraction of product formed at high nucleation and low growth yield, a fine grain size. Following are the cooling rate for the structure with typical industrial process. At 10 square degrees Celsius per second, we need a fine grain size. We go for chill casting. At 10 power 3 to the 10 power 4 degrees Celsius per second, for very fine grain structure, rapid solidification is done. At 10 to 5 to 10 power 6 metastable crystal structure, or also the 10 power 7 metallic glass. If the parent phase is liquid, we go for splat quenching. So the nucleation and growth is directly related to the heat flow from gas liquid to wall through the solidified layer. So consider this is our eye of casting. So if you cool the cast liquid, it shows three different grain structure easily. At the edge near the liquid walls, it formed tiny particles, small aqueous crystals occur as soon as the liquid metals comes in contact. So as we move towards the center, from this C, small aqueous crystal, there forms different columnar grains from which are called columnar grains, which are long and crystal are perpendicular to the direction of the wall. And if we move to the center, we have larger equiaxed zone, large and undergoes relatively small cooling rate. And so in the casting, usually for nucleation and grain size, we try to use titanium and boron as the nucleating agent to, which are added to promote heterogeneous nucleation in aluminum. We use ferrosilicon to cast iron for the purpose of nucleation of graphite. We can use zirconium to magnesium alloy, suggesting small contact angle during heterogeneous nucleation. Also, it can provide some vibration to promote nucleation. Vibration can be through mechanical or sonic or ultrasonic. The pulse of the vibration causes cavitation in the liquid, which tends to form voids, and due to high pressure, these voids collapse to initiate the nucleation. And the purpose of cooling is we must ensure the liquid does not melt back, which can be done using the constitutional supercooling. These are the graph shown from the composition with the temperature. For the simple phase diagram, we study at two temperature T and T prime. At higher temperature, we directly find the liquid composition, but at the lower temperature, which is far away from the liquidus line, we can find that combination of solid and liquid. So, as the composition of liquid is found to be greater than the composition of ideal average composition, suppose this is the solid liquid barrier, which is very linear, and the transformation from liquid to solid is going to occur. And as we move away from the interface into the solid zone, the composition is almost equal. The average composition is equivalent to the liquid composition as we measured, but actually when we are at the interface, the liquid composition is greater than the average composition we measure. So if we measure the temperature at T prime, we get the liquidus line while calculating. If the line is to be this, but the actual line will go steeply away from the liquidus line. But in the case of supercooling, constitutional supercooling, we promote a supercool by enlarging the interface, and so we get the liquidus line and the actual line showing very small difference in their measurement. Fallback of supercooled solid to liquid is very less. This can be done with any protrusion form on the interface. There are many other things we need to notice while studying this solidification unit. One is the formation of dendrites. If the velocity of interface increase further, the cell tend to grow along certain direction. An example, direction 100 for the cubic metals, because the direction 100 is mutually perpendicular, and so at particular direction the formation of dendrites occurs, and during the directional solidification, when dendrites of neighboring grains grow in same direction, we obtain columnar grains. Example with the aluminum nickel cobalt permanent magnet, it doubles the magnetic energy of the product. And macrosegregation. What is macrosegregation is, during the dendritic growth, the liquid to solidify lasts is in spaces between the dendritic arm. The segregation of solute is known as macrosegregation. The process of heating at high temperature for prolonged times wipes out the macrosegregation and become homogenization. You also need to know the porosity and the inclusions. When the percentage of solid increases, liquid not able to flow freely and compensate for the shrinkage, the strain generated by shrinkage fracture on weak solid. This phenomena is called tearing, and oxides of deoxidizing metal and dissolved gases are called as inclusions. This is an elaborate explanation given to the solidification process with phase change. Thank you for watching. Please like, share and subscribe our videos.